Hello everyone. In this lecture, we will study about the MCQs on linear differential equation with constant coefficient. Here we focus on the complementary function. If the roots m1, m2, m3 and so on mn of auxiliary equation phi of d equal to 0 are real and distinct, then solution of phi of d operating on y equal to 0 is. Four options are provided as given here. Among these four options, now we can see here we have total n number of roots which are all real and distinct. Therefore, according to the complementary function property, we have a first rule for real and distinct root, and according to that rule, your yc is equal to, that is your general solution, equal to c1 e raised to m1x plus c2 e raised to m2x plus and so on cn e raised to mnx. Therefore, your correct option is A option. Okay, here we have just place the value of the roots in the exponents like e raised to m1x, e raised to m2x and e raised to mnx along with combinations of arbitrary constant c1, c2 and so on up to cn. Now look at the second one. In the second example, the roots m1, m2, m3 and so on mn of auxiliary equation phi of d equal to 0 are real if two of these roots are repeated, say m1 equal to m2 and the remaining roots m3, m4 and so on mn are distinct, then the solution of phi of d operating on y is given by these four options are provided. And as you know, when we have real and repeated root, that is here m1 is repeated twice, then according to the second rule of finding or writing complementary function, we have yc is equal to c1x plus c2 e raised to m1x plus c3 e raised to m3x plus and so on cn e raised to mnx. Here m3 to mn are real and distinct roots. Therefore, this is actually a combination of case number 1 and case number 2 of complementary function. Therefore, your correct option is C option. Now let us proceed for the next example. The roots m1, m2, m3 and so on mn of auxiliary equation phi of d equal to 0 are real, and if three of these roots are repeated, say m1 equal to m2 equal to m3 and the remaining roots m4, m5 and so on mn are distinct, then solution of phi of d operating on y equal to 0 is, from these four options, we have to choose any one correct option. And you know, when m1 is repeated thrice, then again by using case number 2 of finding the complementary function, we have yc is equal to c1 x square plus c2 x plus c3 e raised to m1 x plus c4 e raised to m4x plus and so on cn e raised to mnx. Here as m1 is repeated thrice, we have a combination of first three terms as given here, and remaining all the roots are distinct roots. Therefore, this is again a combination of case number 1 and case number 2 for real roots. Okay, therefore your correct option is B option. Now let us proceed for the next fourth example. Here m1 equal to alpha plus I beta, m2 equal to alpha minus I beta are two complex roots of auxiliary equation of second order differential equation phi of d operating on y equal to 0, then its solution is any one option from these given four options. And we know for imaginary or complex roots which are distinct, okay, we have a complementary function given by case number 3 of writing complementary function, that is yc is equal to e raised to alpha x into c1 cos beta x plus c2 sin beta x. Okay, where alpha is a real part of a complex root and beta is the imaginary part. And therefore, the correct option is a D option. Now let us proceed for the fifth example. If the complex roots m1 equal to alpha plus I beta and m2 equal to alpha minus I beta of auxiliary equation of fourth order differential equation phi of d operating on y equal to 0 are repeated twice, then its solution is one of these four options provided. And as we know, by using case number 4 of finding the complementary function, we have complex root which are repeated twice. Therefore, the complementary function is given by yc is equal to e raised to alpha x, c1x plus c2 cos of beta x plus c3x plus c4 sine of beta x. Okay, where alpha is your real part and beta is the imaginary part of a given complex roots. Therefore, correct option is B option. Now look at the sixth example. The solution of the differential equation d square y upon dx square minus 5 dy by dx plus 6y equal to 0. Okay, you know, very first we have to consider the auxiliary equation, and by assigning d by dx as a capital D, the auxiliary equation for the given differential equation is d square minus 5d plus 6 equal to 0. Okay, by using factorization method, we can factorize this quadratic equation as d minus 2 into d minus 3 equal to 0. Okay, if I equate each of the factor with 0, we get d equal to 2, 3 as a real and distinct roots. Therefore, by using case number 1 of complementary function for given real and distinct roots, the y that is equal to yc is equal to c1 e raised to 2x plus c2 e raised to 3x. Here we just substitute the values of the real and distinct root in the exponents of the given two terms. As the degree of the given differential equation is 2, we observe here two constants in the general solution or complementary function of this given example. Therefore, the correct option is D. Now let us proceed for the next example. The solution of the differential equation d square y upon dx square minus 5 dy by dx minus 6y equal to 0. Right. Again, assigning d by dx equal to capital D and writing the auxiliary equation for the given linear differential equation, we have d square minus 5d minus 6 equal to 0. This quadratic equation can be factorized into the two factors, namely d plus 1 and d minus 6, that is equal to 0. Okay, equating one of the factor with 0, what we get? D plus 1 equal to 0 and d minus 6 equal to 0. And this gives us what? D equal to minus 1 and d equal to plus 6. Again, these are real and distinct roots. Therefore, by considering case 1 of finding complementary function and just writing this real and distinct root in the exponent, we get a required complementary function that is equal to general solution for given example, and that is equal to c1 e raised to minus x plus c2 e raised to 6x. Therefore, our correct option is A option, c1 e raised to minus x plus c2 e raised to 6x. Now, example number 8. The solution of the differential equation 2d square y upon dx square minus dy by dx minus 10y equal to 0 is. Again, here assign d by dx equal to capital D and consider the auxiliary equation, that is 2d square minus d minus 10 equal to 0. Fine. As here coefficient of d square equal to 2, I have done here one arrangement that minus d is written in the form of 4d minus 5d. Okay. Now, see, from the first two term, we can take 2d common, and again from this last two term you can take minus 5 common. Therefore the term obtained here is what? 2d into d plus 2 minus 5 into d plus 2 equal to 0. Now among these two terms, again I can take d plus 2 common. Therefore in the another bracket we have 2d minus 5 equal to 0. The product of these two terms equal to 0, right? When I compare each of the term with 0, from the first term I get d equal to minus 2, and from the second term we get d equal to 5 by 2. Therefore, here nature of the roots are real and distinct. Therefore, by again using the case number 1 for writing the complementary function, we have y equal to yc, that is equal to c1 e raised to minus 2x plus c2 e raised to 5 by 2x. Here I have kept the values of the roots in the exponent, and therefore the correct option among these given 4 options is C option. Okay, now see the next example. The solution of the differential equation d square y by dx square minus 4y equal to 0 is, from this 4 option, one option is obviously correct. Therefore, we have to first consider the auxiliary equation, and by assigning d by dx equal to capital D, we have the auxiliary equation d square minus 4 equal to 0, right? When I shift this minus 4 on the right side, we have d square equal to plus 4, and taking the square root on the both sides, we get d equal to plus and minus 2. Therefore, again, here roots are real and distinct. First root is plus 2 and second root is minus 2, right? Therefore, again, by using the case number 1 for writing complementary function, we have yc is equal to y equal to c1 e raised to 2x plus c2 e raised to minus 2x. Here again, I have kept these roots in the exponent. And as you know, it is quadratic equation. The total number of arbitrary constants in the given general solutions are 2. Okay. Therefore, the correct option is D option. Now let us proceed for this 10th example. The solution of differential equation d square y upon dx square minus dy by dx minus 2y equal to 0 is. Okay, again here assign d by dx equal to capital D and consider an auxiliary equation d square minus d minus 2 equal to 0. By using factorization method, we can factorize this quadratic equation as product of two factors. First factor is d plus 1, the second factor is d minus 2. And when I equate it with 0, we can write down the value of d equal to minus 1 and d equal to 2. These roots are real and distinct. Therefore, by using case number 1 of complementary function, we have yc is equal to y equal to c1 e raised to 2x plus c2 e raised to minus x. Therefore, correct option is B. Now look at the 11th example. The solution of differential equation 2 times d square y upon dx square minus 5 dy by dx plus 3y equal to 0 is. The 4 options are provided as given here. Now again, by assigning d by dx equals to capital D, we have an auxiliary equation 2d square minus 5d plus 3 equal to 0. In order to obtain the factors for given quadratic equation, I just split this middle term minus 5d as minus 2d minus 3d. Okay. And by taking 2d common from the first two terms, we get 2d times d minus 1. Minus 3 is taken common from the second last two terms. Therefore, here we get minus 3 times d minus 1 equal to 0. Among these two terms, again, I have taken d minus 1 common. Therefore, in the second bracket, we have 2d minus 3. The product of these two brackets equal to 0, right? Therefore, we just compare each bracket with 0 and therefore we get from the first term we have d equal to 1. From the second bracket we get d equal to 3 by 2. Therefore your roots are real and distinct. Now according to the first case of finding complementary function, we have yc is equal to y equal to c1 e raised to x plus c2 e raised to 3 by 2 x. Therefore, our correct option is A option. Now let us look at the 11th, 12th number example. The solution of differential equation d square y upon dx square plus 2 dy by dx plus y equal to 0 is. Again, 4 options are provided. Again, assigning d by dx as a capital D, we have an auxiliary equation d square plus 2d plus 1 equal to 0. This equation represents square of d plus 1. Therefore, what we have here, d plus 1 whole square equal to 0. And this is giving us d plus 1 equal to 0 2 times. Okay, therefore, here we have d equal to minus 1 as a root. Therefore, roots are real and repeated twice. By assuming case number 2, for writing the complementary function, we have y equal to yc is equal to c1x plus c2 e raised to minus x. Therefore, C option is correct from the given 4 options. Now consider the example number 13. The solution of differential equation 4d square y upon dx square minus 4 dy by dx plus y equal to 0 is. Again, 4 options are provided. Again, assigning d by dx as a capital D, we have an auxiliary equation 4d square minus 4d plus 1 equal to 0. Here, in order to obtain the factors for this quadratic equation, I have written this minus 4d as minus 2d minus 2d. Okay, and therefore by taking 2d common from the first two terms, we have 2d times 2d minus 1. From the last two terms, minus sign is taken common. Therefore, in the bracket, we have 2d minus 1. Again, by taking 2d minus 1 common, we get in another bracket 2d minus 1. Just by equating these two terms with a 0, we get d equal to 1 by 2 and d equal to 1 by 2. Here again we are getting real and repeated root. The root d equal to 1 by 2 is repeated twice. Therefore, complementary function or general solution for the given linear differential equation with constant coefficient is obtained by using case number 2 of writing the complementary function that is given by y equal to yc equal to c1 plus c2x e raised to 1 by 2 into x. Therefore, among the given 4 options, D option is correct. Now, next example number 14 is what? The solution of differential equation d square y upon dx square minus 4 dy by dx plus 4y equal to 0 is. Again, 4 options are provided here. Here we again consider d by dx equals to capital D. With this substitution, our auxiliary equation is what? D square minus 4d plus 4 equal to 0. This is the square of the d minus 2 term. Therefore, when I compare d minus 2 equal to 0, it is for 2 times. This gives us d equal to 2 comma 2. Therefore, roots are real and repeated twice. Therefore, by using the second case of writing complementary function, our general solution y equal to yc equal to c1x plus c2 e raised to 2x. Therefore, correct option is A option. Now in example number 15, the solution of differential equation d square y by dx square plus 6 dy by dx plus 9y equal to 0 is. Here the auxiliary equation is d square plus 6d plus 9 equal to 0. It is the square of d plus 3. Therefore, when I compare d plus 3 equal to 0 two times, we have d equal to minus 3, minus 3 as a roots which are real and repeated twice. Therefore, the complementary function is obtained by using case number 2 of writing complementary function, and this gives us y equal to yc is equal to c1x plus c2 e raised to minus 3x. Therefore, correct option is B option. Now in example number 16, to find out the solution of the differential equation d square y upon dx square plus y equal to 0, the auxiliary equation is d square plus 1 equal to 0. When I shift this plus 1 to the right side, it becomes minus 1. And when we take the square root on the both sides, we get this kind of term. Here d equal to plus minus square root of minus 1. But as we know, square root of minus 1 is imaginary unit that is denoted by I. Therefore, d equal to plus and minus I. These are the conjugate roots and these are complex and distinct roots, where the real part alpha equal to 0 and the imaginary part beta equals to 1. Now by assuming case number 3, for writing complementary function when we are having complex and distinct root alpha plus minus I beta, what do we know? We know that yc is equal to e raised to alpha x c1 cos of beta x plus c2 sin of beta x. By using the value of alpha equal to 0 and beta equal to 1, we obtain the final solution or general solution as e raised to 0x c1 cos x plus c2 sin x. Here e raised to 0x is 1. Therefore, y equal to c1 plus cos x plus c2 sin x. That is C option is correct. Now look at the example number 17, where we have to find out the solution of the differential equation d square y upon dx square plus 9y equal to 0. These four options are provided. Here again, the auxiliary equation for given linear differential equation with constant coefficient is d square plus 9 equal to 0. When I shift this plus 9 on the right side, it becomes minus 9. Taking the square root on the both sides, we have such kind of arrangement d equal to plus minus square root of minus 9. Here again, we can observe square root of 9 is 3 and square root of minus 1 is I. Therefore, here we obtain the roots d equal to plus or minus 3i. These roots are complex and distinct with real part alpha equal to 0 and the imaginary part beta equals to 3. Therefore, by referring case number 3 for writing the complementary function when we are having complex and distinct roots, we can write down the complementary function y equal to yc is equal to e raised to 0x c1 cos 3x plus c2 sin 3x. Here again, e raised to 0x is equals to 1, and that is why your correct option is D option, that is equals to c1 cos 3x plus c2 sin 3x. Now in example 18, to find out the solution of the differential equation d square y upon dx square plus dy by dx plus y equal to 0. These four options are provided. Now again, what is auxiliary equation for this given differential equation? By assigning d by dx equal to capital D, we have the auxiliary equation as d square plus d plus 1 equal to 0. Fine. Now it is a quadratic equation whose factors are not possible to find by using factorization method. Therefore, we try for using the quadratic formula. The quadratic formula For the quadratic equation, x square plus bx plus c equal to 0 is written here, where the roots are obtained by formula d equal to minus d plus minus square root of b square minus 4ac upon 2a. By finding the values of a, b and c, here we have a equals to 1, b equals to 1 and c equal to 1. Therefore, d equal to minus 1 plus minus square root of 1 square minus 4 into 1 upon 2 times 1. Okay. Therefore, here in the square root, in the radical sign, what we have? 1 square is 1. 1 minus 4, that is equals to minus 3. Again, you know what? Square root of minus 1 is I. Therefore, what we get? We get d equal to minus 1 by 2 plus or minus root 3 by 2 I, after by separating the denominator. When we observe the nature of the roots are imaginary or complex, and they are distinct with a real part equal to alpha equal to minus 1 by 2 and beta equals to root 3 by 2. Therefore, by assuming case number 3 for writing the complementary function, we have y equal to yc is equal to e raised to minus 1 by 2x into c1 cos root 3 by 2x plus c2 sin root 3 by 2x as a general solution. Therefore, the correct option is C option. Now look at the example number 19. Here, to find out the solution of the differential equation d square y upon dx square plus 6 dy by dx plus 10y equal to 0. Here again 4 options are provided. The auxiliary equation for the given linear differential equation with constant coefficient is d square plus 6d plus 10 equal to 0. Again, here it is not possible to find out the roots by using factorization method. Therefore, we use the quadratic formula for this quadratic equation with value a equals to 1, b equal to 6 and c equal to 10, and using it in the formula minus b plus minus square root of b square minus 4ac upon 2a, we have d equal to minus 6 plus minus square root of b square minus 4 times 10 upon 2 times 1. Okay. Therefore, in the radical sign, we have 36 minus 40, and that 36 minus 40 becomes minus 4. And you know, square root of minus 1 is I and square root of 4 is 2. Therefore, what do we get here? D equal to minus 6 plus minus 2I upon 2. After separating the denominator, you can see here we have minus 3 plus minus I as a root. These roots are complex numbers and a distinct root. Therefore, again by using case number 3 for writing the complementary function with real part alpha equal to minus 3 and imaginary part beta equal to 1, we have complementary function y equal to yc is equal to e raised to minus 3x into c1 cos x plus c2 sin x. Therefore, correct option for given example is A option. Now look at this example number 20. To find out the solution of the differential equation, 4 times d square y upon dx square plus 4 dy by dx plus 5y equal to 0 is. These 4 options are provided. Again, by assigning d by dx equal to capital D, we have an auxiliary equation 4d square plus 4d plus 5 equal to 0. Here we can use the quadratic formula with a equals to 4, b equals to 4 and c equal to 5. Therefore, d equal to minus 4 plus minus square root of 4 square minus 4 times 5 upon 2 times 4. In the square root, what we have? 16 minus of 80. Therefore, it is equal to square root of minus 64. And you know, square root of minus 1 is I and square root of 64 is equal to 8. Therefore, here we have d equal to minus 4 plus minus 8i upon 8. And after separating out the denominator, Here we get the first term as -1/2 and the imaginary part becomes I. Okay, therefore, these roots are again imaginary or complex and distinct with real part equal to -1/2 and imaginary part equal to 1. Therefore, your complementary function y equal to yc equal to e raised to minus x/2 c1 cos x plus c2 sin x. Therefore, correct option is a B option.